Welcome to my presentation, which is about the use of normalized passivity control in hardware in the loop with contact. My name is Christina Insam and I am a PhD student at the Technical University of Munich. I have the honor to present the work that I did together with Hashan Peiris and Daniel Rickson. You might all agree that testing of components during the development process is important in order to have a targeted and fast development, reduce costs, and receive products with high quality. During the test procedure, we can find out potential failure of parts or dynamic behavior that was not intended. An example would be noise vibration harshness problems. In this work, we focus on mechanical applications where contact occurs. Contact is a phenomenon that is often unwanted and leads to unfavorable system dynamics, such as high-frequency oscillations. For example, there is contact between the pantograph and the overhead line of the power supply of a train. Another example is the contact between the landing gear and the ground at the moment of touchdown. The landing gear has to permit safe and comfortable landing. Hardware in the loop is a method to test components already during the development stage under realistic conditions. The idea is to test critical parts experimentally, and the rest of the structure is simulated in a co-simulation on the computer. With this approach, the dynamics of the whole dynamical system can be investigated. We work with a method called hardware in the loop on mechanical level, or also often referred to as real-time hybrid simulation. In this hardware in the loop approach, displacement and force information are exchanged in real time at the interface. This idea can be illustrated using the signal flow diagram known in control theory. What we want to investigate are the dynamics of the overall dynamical system. The whole system consists of the numerical simulation with transfer function g_num and the experimental part with transfer function g_exp. On the previous slide, I already mentioned that we have to couple the two parts at their interface, and the coupling is done using the so-called transfer system. This transfer system consists of an actuator, a force-torque sensor, and a digital signal processor. The actuator receives a desired displacement from the numerical simulation and performs it. The force-torque sensor measures the force response of the experimental part to that displacement. The dynamics of the force-torque sensor can often be assumed to be ideal. However, the actuator is not infinitely fast, and instead of the desired movement c, it performs the movement c'. So, instead of the dynamics of the numerical and the experimental part, there are also additional dynamics. These dynamics make the test outcome inaccurate. What is even worse is that these additional dynamics can make the coupling also unstable, which means that the actuator command starts to oscillate with growing amplitude. It has been found out that these additional dynamics act like negative damping. This means that the damping in the overall system, consisting of the numerical and the experimental part, has to be larger than this negative damping coming from the transfer system. So, if the investigated system is only lightly damped, the actuator has to be fast, such that the test remains stable. The mechanical system that we use for our hardware-in-the-loop tests is this one-dimensional mass spring damper system. This system should represent any mechanical system where contact occurs, but we don't have a certain application in mind. In this system, the lower mounting performs a sine trajectory such that the upper mass comes into contact with the ceiling intermittently. We say that the contact phenomenon is the critical event that is difficult to model and should be investigated in the test. So we split our system into the experimental and numerical part. We use a Stewart platform as transfer system, and you can see the force-torque sensor here. In any hardware-in-the-loop test, there is a physical quantity that one is interested in. This quantity is called quantity of interest. In our case, we say that we are interested in knowing the displacement of the interface over time, which is the displacement of the numerical mass c_num. The only damping that is in this system is the numerical damper dnum. If you remember the previous slide, I told you that the smaller the damping value, the faster the actuator has to be such that the test remains stable. I want to visualize the system behavior on this slide. The damping value is chosen low, such that the test becomes unstable during the contact phase. On the right, you see the real hardware-in-the-loop test, and on the left, the data from this test are visualized in an animation. Instability means that the amplitude of the oscillation increases. In this hardware-in-the-loop test, the instability only occurs during contact, but the test is stable during the non-contact phase. So the question is how we can achieve stable hardware-in-the-loop tests even if the system that we investigate is only lightly damped. For this purpose, we make a short journey to the field of teleoperation. The idea of teleoperation is to control a robot that is in a remote environment, for example undersea or in space. And this remote robot is controlled by a user with a joystick. The manipulator performs the movement and interacts with the environment, and the user receives visual, audio, or a force feedback. In teleoperation, the obstacle is that communication can take a considerable amount of time, and that the remote environment is uncertain. Among others, these factors can make the controller in teleoperation unstable. So researchers made use of the concept of passivity. Passivity is a sufficient criterion to guarantee stability, and it says that the rate of change of energy inside the system must be smaller than or equal to the power that is supplied to the system. This condition basically says that a system is passive if it does not generate energy on its own. Let's have a look at the power flow in a teleoperation system. The teleoperation system is a network consisting of the human operator, who gives inputs to the teleoperator, and the teleoperator which interacts with the environment. This kind of diagram shows the power flow in this network. All connections indicate that there is a power exchange between the respective parts. We want to find out whether the whole network is active or passive. It can be assumed that the human operator and the environment are passive, which means that they cannot become unstable. So the only system in this network that can possibly become active and thus make the whole network unstable is the teleoperator. The passivity controller is included in the bilateral controller, and it observes if the teleoperator is active. If the teleoperator is active, then the passivity controller is activated and introduces a dissipating element that tries to make the teleoperator passive again. We can compare the network structure of teleoperation systems with the hardware-in-the-loop network structure. And what researchers found out is that they are very comparable. The numerical part and the experimental part are mechanical structures that remain passive at all times. But due to time delay and on dynamics, the transfer system can become active and make the coupling unstable. Since the structure is similar and passivity control proves successful in teleoperation, researchers implemented passivity control also for hardware-in-the-loop. Normalized passivity control is one of the applied passivity controllers in hardware-in-the-loop. Until now, it proved to be helpful for hardware-in-the-loop tests where systems with continuous dynamics are investigated. In this work, we investigated whether this kind of passivity controller also proves successful for applications with contact. In normalized passivity control, we have a passivity observer that observes the power flowing from the numerical part to the transfer system and the power flowing from the transfer system to the experimental part. If the power flowing to the experimental part is larger than the power coming from the numerical part, the passivity controller is being activated and the measured force is augmented by a damping force Fd. If the error power is smaller than 0, the transfer system is passive and the passivity controller does not interfere. But if the error power is larger than 0, then the passivity controller introduces a damping force Fd. The damping force is calculated using the time-varying damping constant alpha. The damping constant is calculated by the damping scaling value Gp and the ratio between the error power and the total power in the system. The damping scaling value is the only parameter that can be tuned by hand, and its correct choice is important for the function of the normalized passivity control, which you will see in a bit. We implemented the normalized passivity controller and wanted to find out whether it also works for our application with contact. Remember how the experiment was without passivity control. The hardware-in-the-loop test was unstable during the contact phase, which was visible by oscillations. Now you can see the results with a passivity controller. As you can see, the oscillations can be damped, and the passivity controller proves successful also in this application with contact. You might agree that the video looks nice and that the passivity controller does its job. Nevertheless, we investigated the influence of the passivity controller on the hardware-in-the-loop test in more detail. Remember that the passivity controller introduces a damping force, and this additional damping changes the investigated system dynamics. The goal in hardware-in-the-loop is not only to have safe tests, but also to have accurate tests with high fidelity. Fidelity means that the test replicates the true system dynamics. The reference is usually a measurement of the overall system. We analyzed our hardware-in-the-loop test with the displacement of the interface point as our quantity of interest, C_num. We take a pure simulation of the overall system as our reference. Usually, in a real hardware-in-the-loop test, such a reference simulation is not available because the experimental part is too complex to simulate. However, our system is quite easy to simulate. The fidelity measure that we set up is this relative root mean square error between the solution from the reference simulation and the hardware-in-the-loop test outcome. We investigated the system behavior for different Gp values of the passivity controller, and we also varied the damping value d_num in the dynamical system. The small damping value of 50 kilograms per second corresponds to the videos that I showed before, and you could see that the hardware-in-the-loop test is unstable. For 150 kilograms per second, the hardware-in-the-loop test is stable. Let's have a look at the error energy. The error energy is the sum of the error power over all time steps of the hardware-in-the-loop test. So it measures how much energy has been introduced or dampened by the transfer system throughout the test. Ideally, the transfer system does not have an influence on the test, meaning that the error energy is zero. A negative value means that the transfer system introduced damping, and a positive error that it introduced energy and made the test unstable. We performed the test for all three systems and varied the damping scaling value. We first have a look at the blue line, which stands for the unstable system. For small damping scaling values, the error energy that is introduced by the transfer system is positive. This means that the test was unstable. But we can see that above a value of about 1000 kilograms per second, the error energy is close to zero. This means that the passivity controller dampened the energy that was introduced by the transfer system sufficiently. This is what you could see in the video before. Now we have a look at the green graph, which represents a stable system. We can see that also here the passivity controller managed to dissipate energy in case the transfer system introduced some. In this plot, it is interesting to see that if the damping scaling value becomes too large, then all graphs show negative values, meaning that the transfer system, including the passivity controller, dampened energy rather than introduced some. Finally, I show you the relative root mean square error, which visualizes the fidelity of the test. Here we can see that the passivity controller managed to improve the fidelity of the hardware-in-the-loop test for the unstable system. The fidelity of the stable system is not affected by the passivity controller. Remember that a relative root mean square error of 0 would mean that the test perfectly replicates the true dynamic behavior of the overall system. This is the case for an ideal transfer system. To summarize, we could show that normalized passivity control also performs well for hardware in the loop with contact. There is an appropriate value of GP that is experiment specific and must be tuned by hand. If the value is chosen too high, the transfer system can even introduce damping. What is important to notice is that passivity control only guarantees stability of the test, but does not improve the fidelity. Therefore, the passivity controller could be extended with a control scheme that improves the actuator tracking performance in order to have a higher fidelity of the test. Thank you for watching the video. I would be very happy to answer your questions, and I'm also interested to hear your comments.